What does a speedometer, climbing a mountain, and finding the steepest point on a curve have in common? They all involve differentiation, one of the most powerful tools in mathematics. Let's discover what it really means. Imagine you're standing on a curved hill. How steep is it exactly where you're standing? For a straight line, finding slope is easy, rise over run. But curves are tricky. The slope keeps changing. This is the problem differentiation solves. For a straight line, we can easily calculate slope as rise over run, but for curves, the slope changes at every point. Let's start with what we know. Between 2 points on our curve, we can draw a secant line, just a fancy word for a line cutting through the curve. The slope of this secant line is the average rate of change between these points. The slope is rise over run. The rise is f of x plus h minus f of x, and the run is h, the horizontal distance. Here's the key insight. What if we make h smaller and smaller? Watch what happens as the second point gets closer to our original point. The secant line starts to hug the curve more tightly. It's becoming a tangent line, a line that just kisses the curve at exactly 1 point. If we zoom in close enough, every smooth curve looks like a straight line. The slope of that line is what we call the derivative. This gives us the formal definition of the derivative. The derivative of f at x, written f prime of x, is the limit as h approaches 0 of this fraction. We're not dividing by 0. We're asking what value this fraction approaches as h gets infinitely small. We can also write this as di dx or df dx, representing the instantaneous rate of change. Let's put this into action. We'll find the derivative of f of x equals x squared using our definition. Following our process, substitute, expand, simplify, factor, and take the limit. We get the derivative of x squared is 2x. So the derivative of x squared is 2x. This means at any point x, the slope of the curve is 2 times x. Let's try one more, finding the derivative of x cubed. Following the same process, substitute, expand, simplify, and take the limit. We get the derivative of x cubed is 3x squared. Notice at x equals 0. The slope is 0. The curve is flat. At other points, the slope depends on x squared. Notice the pattern. For x to the power n, the derivative is n times x to the power n minus 1.